Hello, my name is Edwin Török, and I'll be presenting about a tool that I wrote to detect bugs in the OCaml C bindings in Xen. I titled my talk Removing Gremlins. It's a reference here that sometimes these race conditions are referred to as bugs or gremlins or hard to debug things. And it also goes with the theme that I use this static analyzer framework, which is called Goblint. So it sort of goes with that theme. I'm working at XenServer, which is proud of cloud software group. I've been working there for 6 years now, mostly on the control plane and performance parts of the XenServer tool stack. So XenServer uses Xen hypervisor and the Zapi project, which are open source projects, and it adds a few more things, and it's a commercial distribution that customers can use, and they can buy support, and we develop an API that basically allows you to orchestrate and manage virtual machines using Xen. So here's what my talk will be about. First, I'll give some examples of how OCaml and C are used in Zapi and the Xen project. Then I'll give a few examples on why this interface between OCaml and C is actually more unsafe than either of those languages taken alone, which might seem a little bit surprising at first, because you would expect that in worst case it will be as good or as bad as C itself, but there are actually some aspects that you would take for granted when developing C code that are missing from this interface. And I'll give a few examples of actual bugs we found or we accidentally introduced in the Xen code base. Those bugs are fixed now, but it's good to have a tool to automatically detect those kinds of bugs. Developing such a tool that proves the absence of all bugs would, of course, take a very long time. So the approach that I've taken here is to incrementally develop the tool, focusing on the exact bug that I wanted to avoid, right? So instead of having a tool that can prove that everything is correct, which is a very challenging task, I would incrementally develop the tool and teach it about more and more rules, more and more about safety rules, until at some point in the future we would reach a place where you can run it and say, okay, this has no bugs that it can find. But by this incremental approach, it means that the tool is immediately useful, right? So it can find these few bugs that we know about, and we can extend it in the future. It's built on a static analysis framework, so there are some theoretical foundations on which it builds, so it can be extended in the future. One common problem with static analyzer tools is that you may get lots of false positives, and then developers are less inclined to go through all the false positives to find the few that may be relevant. So especially if you want to run this in a continuous integration system, then the goal would be that as a starting point, you would want to have 0 warnings or errors. And then from that point on, you take care not to introduce more warnings or errors. So I reduce the scope of the bugs that I want to find to just those that once we eliminated the known bugs, we are not left with any false positives in the CI. So here are examples of a few components that we have in the Zapi tool stack on the left-hand side. They are written in OCaml. Then we have some bindings, which is an interface between the OCaml code and the C code. And there are some C libraries that they use. Some of them target the operating system, some of them target the hypervisor itself. So we have components like XenOps-D, which coordinate building a domain, everything that has to do with the lifecycle of the domain itself. Few helper tools that look at statistics, so those are all the RRD tools. We also have OXenStore-D, which is the XenStore server implementation, which is technically part of Xen, but it's written in OCaml, and a few other libraries. And the bindings are for like the event channel stubs, all the Xen control stubs, and various operating system stubs like syslog, and also access to the ring buffers, and such. The mailing link, libc, systemd, libzen control, libzen event channel. So there is a way to write an OCaml to C binding. At the beginning, you had to write all of these by hand. So you write a declaration in OCaml. I'll show an example in a moment of how that looks like. And you write a small function in C that handles that bridge between the two languages. But if you look at the properties of the system, you'd want some memory safety properties and also type checking, right? So we take type checking for granted in OCaml, and in C as well, you have type checking. So of course, type checking doesn't guarantee that your program functions correctly, but it does eliminate quite a large number of very easy to make bugs, like you call the function with the wrong number of arguments. And you have that both in OCaml and in C. But in this interface between OCaml and C, you don't have that, because the OCaml compiler is not aware what you've written in C, and your C compiler is not aware what you've written in OCaml. So each of them type checks their own code, and you link it together, but there are no checks either at link time or at compile time for even basic properties like did you call it with the right number of arguments. Obviously, when you run it at runtime, it would then crash if you called it wrongly. And you may think, okay, that's something, okay, you write it the first time, you test it, and then you don't have to worry about it anymore. But code evolves, right? So you make changes to the code, you refactor C code, you refactor OCaml code, and if you're not careful, then you introduce bugs, and we'll have an example about that shortly. And because you don't have these properties, you have to check them manually. And there are so many of these properties and the interaction between these functions, it's very hard to keep it in your head when you're trying to do code review, because you don't look just at the code that has been changed. You need to look at how that code interacts with the part that you don't see in the diff, and there will be an example about that shortly. There are also problems with use after free. So in OCaml, you don't have use after free because it's a garbage collected language, and you only release memory when nothing uses it. And again, if you're not using multithreading in OCaml itself, you have a data race free property, and even if you have data races, there's a property that the data race is constrained to the module containing it and doesn't affect the rest of the code. But again, you don't have that property on this interaction between the OCaml and the C side, because one side is not aware about the other. So there are a few links here to the manual. There's a description of what rules you should follow when writing this code, but let me just quickly show an example of how such an interface looks like, so it's more obvious what the problems could be. So here is an example of a binding to the ncurses library. The way you declare it, you put the external keyword and then the name of the C function, and this is the declaration of the OCaml function. That's a type declaration in OCaml. So these are all the functions that you declare. And then here would be the actual implementation. So for each function in OCaml, you have one function in C. So you don't call the ncurses library directly. You call this sort of glue code, or we also call it stub function. It receives the OCaml value, does some minimal transformation on it, calls the C function, and does some minimal transformation on the way back. Now, if your value is void, obviously you don't do any transformation at all, but you see here you take some number of lines, number of columns as argument, and those are integer, and you need to transform it. And you already here, you see the lack of type checking. So everything you receive here in this C stub is of type value. And there's no distinction between integers and pointers or strings. So you have to know what type you sent on the OCaml side so that it matches with what type you sent on the C side. Obviously, these are macros, and they would allow you to do just about everything. You can insert some assertions where you can check the tag of the value. So is it actually an integer before I dereference it, or is it actually a string before I dereference it? But by default, it doesn't do any of that. And also, you have a number of arguments here. You see this one has 4 arguments, but there's nothing checking that you actually declared 4 arguments on the OCaml side. So you could have more, you could have less. So all of this makes it quite difficult to review a patch because, for example, you could you could get a change like this, that someone goes and changes the C function, maybe to match something that was changed in the XenC libraries, and they don't touch the OCaml code, maybe because they are not aware that it's there, or they would assume that, okay, they would get a compiler error if they get something like this fundamentally wrong. But that's not the case, and actually this bug has been in the Xen code base for quite a long time. And because this particular binding wasn't even used, so XenObsD had its own copy, which happened to be correct, it went unnoticed until I actually tried to see, can I use the upstream version of the binding? And then I've seen, okay, it's not actually written correctly. And now this kind of bug can be detected by my tool. And essentially, you don't even need static analysis or any kind of complicated analysis to detect these kind of mismatches. All you would need is a header file, right? So you have the OCaml code, you have the C code, and you need the prototype of that function declared somewhere. And if the compiler would give it to you, then the C compiler could do this checking automatically. So that's actually the first thing that my tool does, is generate this header automatically from the OCaml code. So at least one error-prone part is removed from this review process. So I take an ML file as input, I produce a header file as output. This can actually be done in a surprisingly small amount of OCaml code with no external dependencies because you have the OCaml abstract syntax tree library, the compiler libs, shipped with OCaml 4.0. Now, actually, to do the analysis that I do here, I need OCaml 4.08+, because the abstract syntax tree keeps evolving. It's not necessarily always backwards compatible. It might be possible to backport this to older versions of OCaml if there is interest to it. So basically, you run this tool and you get the header file. As a limitation, it only works for bytecode. We'll see later that native code requires a bit more complicated handling because you can have a few more annotations, like you have a few attributes on your functions, like you can say unboxed or noalloc, so that you optimize the way these functions get called. And then, of course, the analyzer needs to emit the correct header file. And it's possible to do that. It requires a little bit more code, so it's around 250 lines. But I need to work with the typed tree, which is the OCaml file compiled and typing information applied by the compiler. But that changes even more frequently. It's a bit more closely tied to the OCaml release. So it's not something that we could use in Xen directly, but it could be a separate tool. And my plan is to first distribute these tools on OPAM, which is a package manager used by OCaml developers, and maybe in the future the compiler itself could have this small tool part of it. I'll have to discuss with the upstream maintainers what they think, because then it would improve the quality of these bindings by default, right? If the tool is there by default, then it's a lot more easier for you to use it. And I think it will be quite easy to keep up with new versions of the compiler, because every time a new attribute gets added, there's probably not even any support that we have to do here, because the type tree already processes the attribute. So it's a very small amount of code that I have to add, okay, what the type of that is. Well, it's probably just a few lines of code every time there is a new version of OCaml released. So we'll see how that works out in practice when new versions of OCaml get released. There is also a unit test for this tool. So the tool, I called it lean C stubs arity. Arity is usually how you refer to the number of arguments. There is an example here. This is the OCaml function, and it generates this header. So this is called a cram style test. So it's essentially a text file. You have some comments in it, so you say what your test does, and then you have something that looks like shell commands. And then you have the output from the shell command. And the commands can be any kind of basic Unix tools that you would expect to be already installed, or it can also be binaries that you have just built in the build system. And then it runs it, and it checks that the output matches. And if the output doesn't match, the build fails, and it prints a diff of what the output actually was. So for very basic properties, you can do like kind of smoke testing that, okay, you don't break the very basic properties, and you can cover the corner cases, because there are quite a few corner cases. They are documented in the manual. So what I intend to do is take a few more of those documentations from the manual, translate them into this sort of executable documentation or executable tests, so that we see that the tool itself works correctly, right? Because we use the tool to verify something else, but yeah, we need something to verify the tool. Okay, so this number of arguments check was fairly easy to do, but you can have a lot more complicated bugs as well. So this is another case where a race condition was introduced. You can see here the patch. The patch itself is fine, it doesn't have any problems, but it affects code elsewhere. So what the patch does is it changes this macro. So previously you've taken an OCaml value and cast it to a C pointer directly. Newer versions of OCaml don't like that, so they call those naked pointers. So you need to wrap all these C pointers inside an OCaml value. And that's called a custom value. And you use this other macro to then extract the C pointer out. So this all looks fine. The problem is when you have multiple threads, because then you have to be a little bit careful. Because when you release your runtime lock, OCaml can run another thread or another thread. And when that thread runs and the garbage collector runs, it can move around the OCaml value in memory. So it can compact the memory, it can release the memory. And then the pointer that you think you had will be a dangling pointer. It will reference something stale in memory. It may not even be mapped. It could be the completely wrong data. So this is the buggy code, actually. So enter blocking section releases the runtime lock, and leave blocking section acquires the runtime lock. So it's a bit awkward to read because it's the wrong way around, because you'd expect this one to release the lock, which is what it does, but it's called from the other perspective, that you enter a section that you'd expect to block for a long time, and then that's why you release the runtime lock, so you allow other threads to run. And you see that this macro is used here. And because initially it was just a pointer cast, right? So that's safe to do. You don't dereference anything. You already have the pointer. It was a C pointer to begin with, so the OCaml garbage collector didn't move it. But now, because it's part of this OCaml value, which may move, it's not safe to dereference it here. So the way to fix it is you use this macro, but you use it before the dereference, right? You put it in a local variable, and then that local variable is a C pointer, which won't move, and then everything will be safe. But we have like hundreds of thousands of these functions, and it's quite error prone to check whether all of them work. So one thing we did, we renamed the macro. So that forces us to check all the call sites. If we happen to leave any of these macros behind, it would fail to compile. But even then you can make mistakes. Like if you just do a simple sed, again, you would be left with mistakes. And that's why I developed this tool that can find these kinds of race conditions. And we'll see later on how the race condition report actually looks like. This is another case where you can have a bug. It's a little bit more subtle because it's C pointers, and C pointers don't move normally, except what we've done here is we use this abstract tag allocation. So abstract tag is a way to tell OCaml runtime, okay, allocate me this many bytes, and don't look inside, right? So it will allocate a little bit more at the tag in front, so OCaml knows to skip it. And inside it, I can store anything I want from C, even a pointer. And then I can get a pointer to this effectively structure that I allocated inside of it. And the problem is with this structure, right? So if I get this and I cast it to a pointer, now whether I do it like this or I use the abstract val interface, this won't be correct, because at the time I dereferenced this interface here, this one actually pointed inside an OCaml value. And the OCaml value may have moved just as I released the lock here. Some other thread may have run and moved it. So it's not safe to do it like this. So the only way is that you never store this cast in a temporary variable. You always use a local copy, right? Because it's not safe to access any part of this value once you release the runtime lock. So you need to use some local values. This one is not actually quite completely modeled in the analyzer yet, but I think it will be possible to detect these kinds of problems, because essentially I need to detect who is an abstract tag and apply this special rule to it. There's a quick intro now on how static analysis works in general. There are many ways to implement it, but for our purposes, what we want to do is keep track of some properties, keep track of some invariants, like our code is safe, and then at each step, we check that we don't break that invariant. So this is usually done using a mathematical structure called a lattice. So you have a bottom value or initial value. You have a top value, which is basically says, okay, I don't know anything about this value anymore. It could be anything. And you can have anything in between. And you have a partial order. So it's not a total order. So all the values are comparable, but they are not, they don't necessarily form a linear chain, right? So you can have like a tree or any kind of other structure there. So you only have a partial comparison. So you could have two values, and you can't say which one is smaller than the other because they're at an equal level in the lattice. We'll see shortly an example of how that looks. But you can say, okay, those values are equal, but you also have values that are higher, values that are lower. And there are these properties with this function that you can find the least upper bound and the greatest lower bound. They're also called join and meet. And if you look at the lattice, which I'll show in a moment, then you move up or down the lattice. Now, if it has a finite height and finite number of elements, then you can compute a fixed point, right? So you evaluate an expression, you get some result, then you plug it back in, and you keep evaluating it until you get back the same value you started out with. And you can also compose these lattices. So you can have a map from variables to values, and that's a lattice too if the abstract values are a lattice. So here is an example for a lattice for keeping track just of the sign of a value. So we don't keep track of the interval or the actual values. We want to do a very simplistic analysis, just is it positive, negative, or 0. So the bottom value, the initial one, means we don't know anything yet. It's uninitialized. Then you can have negative, 0, or positive, and they're not comparable. So neither of them is higher than the other, but they're higher than bottom, right? So it's better to know that it's negative than not know anything. And then there's also top, which happens for join, and you would see that join maps to the union of what happens on an if branch. So on this branch of if you have x minus 5, so x is negative, so the lattice will be minus. Again, x minus 7, the lattice is negative. And then what's the lattice value here? Well, it's the union of the other lattice values. And minus, when you join them, it stays minus. And okay, we know that x is negative, and then this Boolean is always true. But let's say instead of minus 7, you had plus 1 here. Then you have the union of minus and plus. And if you look on this lattice here, you can't compare minus and plus. Neither of them is higher than the other. So the only way to move higher in the lattice is to go to the top. So basically you say it could be either negative or positive. We don't know anymore. And yeah, you could maybe special case 0 if you wanted to. And then you would have like a set of values. You could have maybe minus plus as a set. You could add more values here in the lattice at another level, like all the combinations between minus, 0, minus, plus, and then. But at some point you will have the top value where you say, okay, I can have any combinations when I join these branches, so I can't actually tell you, is it negative or positive. So it doesn't work in all the cases, but in quite a lot of cases, this kind of simplification makes the static analyzer run faster and use less memory, because in general, the static analysis could go like 2 to the power of n. Imagine having n if statements and having to track all the possibilities of those if statements, even if they are just one condition. It very quickly becomes exponential and untractable. So you need these sort of simplifications and unifications where, yeah, those two values are different, but when you unify them, we keep track of a simpler property. And you can also do something more complicated. I have an example here of some more complicated lattices. So there's this library called apron. So you can have box constraints, you can have polyhedra, you can have congruencies. So it's possible to keep track of lots of properties. And the framework already does this from me. So I use a static analysis framework, but I need to know what the framework provides in order to be able to use that framework. There's also an example here on Wikipedia, a bit more complicated, because you need to keep track not just of the sign, but also on whether it's even or odd. And then you can say, okay, I have a division by here, but actually prove it's never division by 0 because of the way it works out in this example. So that's a little bit about lattices. There are a lot of other structures that this framework provides. I have a fixed point solver, I have path-sensitive analysis, so I can choose whether I want to care about which branch the if has taken, or I can choose not to. Code reachability, also function summaries. So again, with functions, you can have this state explosion, but you can say I compute all the post-conditions of the function, all the preconditions, and then that's like the summary of the function, and I'm done with it. And when I call a function, then basically I merge the lattices from that function in what I have. And this allows static analysis to actually proceed quite quickly. There are other approaches based on separation logic, but they are a bit more difficult. I haven't modeled callbacks, so callbacks are quite difficult to model, and actually we removed the code that used it. So maybe in the future, if you want to introduce them back, I'll add something to my static analysis. There's also a tool called OCaml C types, which can make some of this a bit easier because it generates some code automatically, so it solves the header generation problem, but it introduces a problem with handling the lifetime of strings. So you have this function and you give it the start of buff, right? But nothing references buff anymore. So then the OCaml garbage collector will go, okay, nothing references buff, and I'm going to go and free it or move it. Except this start was actually a pointer inside buff, which the garbage collector doesn't know. So you have to do all these tricks to keep it alive. There is this opaque identity which tells the optimizer, okay, don't look inside it, trust me, it's still alive, and to keep it alive. But even if you do that, it's also very tricky. And again, there are no tools to check this. That's one of the main problems. There are no tools to check any of this. So there are more details on the slides about C types. I'm going to skip over them because I want to focus a bit more on the tooling, right? Because on the C side, you have all these tools. So you have GCC analyzer, Clang analyzer, sanitizers, valgrind. You can run valgrind on the OCaml program, but it won't tell you much because it doesn't use malloc free for each allocation, and you won't catch as many bugs, right? So the C tools are not aware of the garbage collector rules, and the OCaml tools are not aware of the C rules. So what I've done, I've written a small tool that can generate sort of a model for static analyzers. So this should also work with other static analyzers, not just the one that I'm using here. I'm essentially generating a small C function that shows how this code could be invoked, right? And that's actually not quite that big. Also, I have a model for the OCaml runtime. So the OCaml runtime, the real one, is quite complex. You have memory mapping and malloc and free and everything. And yeah, you don't need all those details. So I have a small handwritten model of the runtime, which just basically calls malloc and free. And then the static analyzer can check all of this. Also for checking the safety of the locks, it just relies on pthread, and it models pthread for safety. So let me show an example of how this report actually looks like. So I produce, or the static analysis framework that I'm using produces a report in the serif format, which is an XML that's sort of standard and can be used by other static analysis tools. And GitHub Actions can actually render it. So it produces an XML, and this rendering is what you get from GitHub Actions, and it tells you, okay, this is the line, and this is the message here is coming from my tool, says, yes, there is a race condition here. It also has a built-in viewer, which also shows the same kind of error. You don't have to use GitHub Actions. You can do everything locally. And that built-in web UI tool also gives you some debugging information, like about the OCaml runtime log. So there's some future work here, right? So I've done just enough static analysis to find this particular bug. But there is, of course, a lot more that could be done here in the future, and I intend to extend it as we go along. And I've seen all the suggestions about using the GitLab CI, so I'll see if I can port my code that I have here to the GitLab CI, because right now it runs on GitHub Actions, but it's a few commands that you have to run in the right order, so it should be possible to build a container, and then we can probably run it with a bit of work on GitLab. And if we can get this enabled by default, then we can avoid at least the bugs we know about, right? And as the tool evolves, it can also avoid bugs elsewhere. So I intend to deploy this first on Zen and Zappy, and if it works well, then we can maybe talk with other people in the OCaml community to also extend it for other tools in the OCaml ecosystem, and maybe slowly part of these tools could become part of the compiler to make this process a bit less error-prone. So I think we're nearly out of time, but maybe we have time for a couple of questions if anyone has them.
Where can I download the tool from?
Yeah, if you ask.
So where can I download the tool from?
Okay, so there is I should have probably put a link. So right now it's on my branch. It's this private Edwin static 2 branch on GitHub, but I intend to make that part of Zappy master. So we'll review the pull request, and we will make it part of Zappy master. I'll see if I can add the link to the XenSCAD presentation. But it's basically here on GitHub, Edwin Török Zen API, private Edwin 2 stack, static 2. And the way you run it, you use make, test, analyze, and then the tool will itself run. So you run the tool. Let me scroll up to the place the tool runs. Yeah, you run make, test, analyze, and it will analyze Zappy itself. For Zen, it's a little bit more complicated, but I'll add it to the CI.
Okay, thanks.
Yeah.
So I'm quite new to Zen, but how heavily are OCaml bindings used in Zen, like from OCaml C?
So I think there are like a couple of hundred. Actually, I can check here because we have. If I enter shell, I think it was something like 100 or so, a few hundred bindings. So if you look in the source code here, you can see all the bindings that we have. So for XenOpsD, it would be in OCaml. XenOpsD, C stubs, and then these are all the ones in Zen control. So you see it's, this one is like 500 lines. If you look in Zen, you will also find a few bindings in Zen. They are in tools OCaml libs. So you have bindings for Zen nmap, Zen control. So it's mostly the interface with building domains and interface with mapping the channels and mostly everything that XenStore needs. And then everything the tool stack will need. Right? So these are all the functions that are exported. So it's not actually that much, because you see the OCaml code is like 248 lines of code. And yeah, the Zen control stubs again. They're a little bit longer. They're at 1,200 lines of code. But these bindings also interact with each other. And that's what makes it a bit more complicated to use. Do we have more questions?
One more than
yeah.
And it's just that, so this is, you currently use it for Zen API, and how easily would this be extensible to other bindings outside of Zen? Is there like some Zen specific code sitting in there, or can it be like...
So it's not Zen specific. The reason it's built on Zen first is Zen doesn't use all the features from the C foreign function interface in OCaml. There are a few more advanced features that the static analyzer would need to be taught about, that when you run it, on more complicated code elsewhere in the ecosystem it might warn about. So if we teach them about those missing features, then you can run it anywhere. So you can run it on other code as well currently, but you will probably get some false positives because we don't model all the features that you would use. But there isn't anything Zen specific there. It's just that I made it 0 false positives on the kind of code that Zen has.
Next question. So can you use this, for example, for a different GC language, not OCaml, but I don't know, C# to C or any other FFIs that you can use?
So I'm not aware how they work. So not this exact tool, because this exact tool is specific to loading and parsing OCaml. I mean, the principles could be applied to other tools, but I'm not sure how their FFI is done. Do they have the same problems that OCaml has or doesn't have? But for example, if you want communication between OCaml and Rust, there is another project that actually skips going. So one way is you go from OCaml to Rust by going to C, and then from C to Rust, but you can also go straight from OCaml to Rust. And there's a separate project for that, which I'm not involved in, but it looks quite interesting, because you go from one safe language to another without going through an unsafe interface. But yeah, for C#, I don't have any experience on that side. Yeah. I think now it's time for the next presentation. But yeah, if you have more questions, you can probably find me in the hallway.